Hi, thank you all for joining. My name is Sudhakar Bulusu. I'm the Director of Engineering for Productivity Products, which is a Honeywell business that focuses on rugged handhelds, printers, RFID readers, mobile phones, and scanners. So that I'll be talking to you about the IoT and edge devices, which is the topic of the webinar today that's hosted on HackerEarth. And so the agenda that I have in place is this. We'll just look at what is IoT at a very high level, and we'll look at some differences between IoT and industrial IoT, which is a sort of a subset of the entire IoT space. We'll look at the high-level architecture of an industrial IoT stack. Then we'll focus more on the edge device portion of IoT, because IoT is, it spans across the gamut, right, from the sensors all the way to the cloud and analytics. And the focus of the webinar, though, is on the edge devices, and we will talk about that. So what is an edge device? The challenges that one sees in integration of edge devices, the connectivity options, the security part to it, which is increasingly becoming important in IoT. And for those of you who are just beginners or trying to get started on IoT, what are the options out there? There's a plethora of articles and webinars and tools that you can use to get started. And then we'll also talk a little bit about edge devices and the analytics that one could do on the data from the edge devices and on the edge devices themselves. Based on on the data that they have within themselves, and a sample use case that will help you understand how those analytics can be monetized and how people actually use this analytics piece. So, and obviously we will have time for Q&A towards the end. So what is IoT? Everybody knows, right? This is the Internet of Things. So I found a definition from Gartner, which says it's a network of physical objects that contain embedded technology to communicate and sense or interact with their internal states or external environment. Now that's a pretty loaded definition. So, but at a very simple level, if you think about IoT, I just think this is it. You have things, you have the cloud or the internet in between, and this is just connecting all the things to the internet, right? It's as simple as that. Because traditionally, if you look at some of the devices represented in the picture there, they've been around for quite a long time, right? Look at consumer devices like your light bulbs, toasters, refrigerators, I don't know, you can name it, right? Telephones, watches. So they've been around for a long time. The Internet of Things is, the ability to connect all these to the internet, using some communication technology, and then deriving some additional value on that connectivity. Because while it is very good to connect all these devices, why would one choose to do that? So for instance, you would want, if you want some cookies to be baked in your oven by the time you reach home, or you want the air conditioner at your home to turn on before you go home, and so that the room is at a temperature, at your desired temperature. So these are some very simple use cases that one could choose to enable. So that is what, according to me, it's a very simple definition of IoT, right? You connect the things to the cloud and then you derive some benefits out of it. And if you look at the devices, some of the devices represented there, it's both consumer and non-consumer devices, right? It could be virtually any device with some computing power that you can choose to connect to the internet or to the cloud. All right, then coming to IoT, why would you worry about IoT, or why should one care about IoT? I spoke about a couple of benefits very quickly in the previous slide, but let's say you are in the business of crime fighting and you are there have been superheroes. I'm sure a lot of you are comic book fans. And if you look at, there are two classes of superheroes. Right? There is this Superman, Spider-Man, and all these kinds of mutants and with extraordinary abilities. And then there's a class of superheroes like Batman, who don't have any superpowers, but they just rely on technology and maybe some physical strength and martial arts, and go about their business of fighting crime. So if you look at the evolution of superheroes very quickly, I don't know how many of you recognize him. He's Phantom or Kit Walker, Ghost to Walks, right? All he had with him was those two guns that you see in his holster there. And so all he had was his ability to physical strength and these guns which he used to fight crime with. And even for communication, I mean, he lives in a skull cave somewhere in a jungle in Africa, and when there's a communication that needs to go out to him, the jungle tribes and all used to beat drums, and that's how the communication happens with the Phantom, or he's also called the Ghost who Walks. So next, if you see, this is Batman. Very similar. I mean, a billionaire, Bruce Wayne, that's his alter ego. And he's a slightly more advanced version of the Phantom, right? He has a bat belt where he has all kinds of cool gadgets. But still, I mean, this is like computing in the 90s, right? I mean, you had powerful computers, I mean, which are not so powerful now in hindsight, but they were quite powerful. But with very limited connectivity to the outside world. So while Batman goes about with all his cool gadgets fighting crime, I mean, wherever he needs help, he goes back to his bat cave, and then, I mean, probably researchers, he has magically has access to so many records and all that. God knows how he gets them, but so he uses that to fight crime, right? Now, I mean, if you zoom into the future a little more, now you have Iron Man. So he's cool because he can fly, he can do all kinds of things. But the biggest advantage that you would see with Iron Man, I mean, he has an assistant Jarvis. I mean, Tony Stark builds Jarvis, Tony Stark, the alter ego for Iron Man. And all the gadgets in his iron suit, I mean, they're all connected. I mean, if you see real time while he's fighting crime, I mean, he gets real time information. He knows what is the state of his body armor. He knows what is the state of his weaponry. I mean, how much damage can he sustain? I mean, what is his altitude? I mean, all kinds of things, you name it, and somehow magically he has this. And that's the power of connectivity, right? I mean, and that makes him a much more maybe efficient crime fighter as opposed to the Phantom or the Batman, who have to rely mostly on their abilities and some superhuman wisdom or whatever you call it, right? So that is the power of IoT. I mean, the ability to connect things and draw insights from them, and then actionable insights that you can act upon. So I mean, so I thought this is a very nice example to see how you can be very efficient when you have the right information available to you in real time. All right. Now, I was talking about two classes of IoT, right? There is the Internet of Things, and there's a class of Internet of Things called the Industrial Internet of Things. So now if we talk about Industrial Internet of Things, how is it different, right? So one is the category of devices that one chooses to connect. If you talk about a light bulb, a refrigerator, a toaster, an oven, I mean, they're all consumer devices, and they do fall under the IoT space. But when you talk about Industrial Internet of Things, it is industrial devices. I mean, these are things that corporations would use, right? Like you talk about your heating, ventilation, air conditioning systems, your boilers, chillers, thermostats. I mean, surveillance cameras. So if you look at some of these, or it could even be things in oil and gas refineries, your aircraft. So it's a wide gamut of things that you can connect, which fall in the industrial Internet of Things. So what distinguishes IoT versus IIoT? I mean, I just wanted to draw on this difference because if you actually understand the industrial Internet of Things and you start building your capabilities around that, I mean, a lot of them are much easily transferable to IoT than the other way around, right? I mean, IoT, obviously, it has its own challenges in terms of your user experience that one needs to be very watchful of when you're dealing with consumer devices. But when you're talking of edge devices specifically, if you understand industrial Internet of Things, I think that's very beneficial to just doing any kind of IoT. So we can just go through I mean, I've just highlighted a few areas that one needs to focus on. The first one is human interaction. So when you talk about wearables, right? I mean, that's an IoT device. I mean, the wearables that you use for monitoring your health, heart rate, and whatnot. So there's a human interaction there. I mean, you probably look at it, I mean, multiple times a day. I mean, you tap on it, you maybe charge it. So there are a lot of things that, I mean, we interact with when you talk about such devices that are general IoT devices. But in the case of IIoT, I mean, the industrial internet, there is very limited human interaction with the device. For instance, if you have a smoke alarm somewhere set up in your home, very rarely do you ever go and fiddle around with your smoke alarm. I mean, for the most part, it's just there blinking away and probably just sending some data to the cloud, most of which is never visible to you, other than probably the periodic reports that are probably sent to your phone or your email. So that's a very important element when you talk about the details. Once we go into the details of edge devices, this is an important element to bear in mind. The second important element is the environment, operating environment, because when you talk about the edge devices and the device, when you go and deploy these in the field, so it's very unlikely that IoT devices are deployed in very harsh environments. Of course, you talk about, again, I talk about variables because that's something that's so ubiquitous and common these days. You can talk about them being waterproof. You can talk about them surviving a few tumbles, but beyond that, it's very unlikely that they'll be subjected to a wide range of environments or extreme conditions or rapid changes in conditions in a very short period of time. So it's typically a very controlled environment that they are subjected to. But when you talk about IIoT, you don't know where something would be deployed. For instance, if you have, let's say, a oil well monitoring unit, which is, an RT or a remote telemetry unit, that could be installed in a desert, with temperatures over 50 degrees Celsius, and extreme cold, dust. You, the variations in temperature or in the operating environment, it make the device necessarily, the design constraints imposed on the device are that it has to be necessarily rugged. And again, coupled with the lack of human interaction or the remoteness of the installations that they're subject to, so that presents its own unique set of challenges. Then the operating life of devices in the consumer space, where a plethora of the IoT devices are. So the life cycles are pretty short. You keep refreshing the devices so frequently. Nobody uses phones for more than a couple of years or maybe 3 years. Same thing with wearables. The features and the capabilities of these devices advance so rapidly that customers typically end up refreshing these devices very often, which is again not the case with the IIoT, because this is in the industrial Internet of Things. These are companies that are buying these devices. The investments that go into it. And so there has to be a bang for the buck, right? If I go and buy some, let's say some smoke alarms for a building, I would want the smoke alarms to function for over a decade at least, if not more, because what is the necessity for refreshing that technology, and what additional benefit can something new get me? So that there would always be that calculation that goes into spending money when it comes to large scale deployments, and when organizations, because they have to understand the benefit very clearly if they have to shell any additional money for it. So the operating life of these devices is very long, and then that's again dictated by how robust your edge device is, how robust the design is, and how much have you thought about the architecture and the design elements to help you prolong the life and stay current with the technology advances that will anyway happen. So the ability to, for instance, remotely upgrade your firmware, and put new features in. So all those, there's a lot of architectural decisions that need to be taken, because it's very hard to reverse some fundamental decisions that you take at the beginning. Then the other important piece, which is applicable both for, on devices either in IoT or the IIoT, but especially in IoT, is access to power supply. A lot of the devices in the consumer space, you can typically, most of them are battery operated, right? And one of the things is you can always go and recharge your wearable, right? You can recharge it maybe once in 2 days, once in 4 days, or whatever you need to. Maybe it's an irritation if you have to recharge it more, but there's nothing there's no fundamental constraint in the number of times you can go and recharge. And in many cases, probably it'll be plugged into a mains, like a refrigerator. It is plugged into the mains power supply, and you typically don't have a constraint when it comes to power. But again, when it comes to IIoT, power supply is a constraint. In many cases, you would probably be operating on a battery somewhere. For instance, the example that I just alluded to about monitoring oil wells. So if it is a device that's somewhere out there, which is probably transmitting some data from an oil well out, it's very unlikely that they have access to any mains power. So in some cases, maybe it's a solar power panel that is feeding power to your unit, and at night, this energy gets stored in a battery, and probably that is the power source for the rest of the time when there's no solar energy. So when you talk about such environments and conditions, it's highly important for you to consider the low power aspects of your design, because there is very little you can do to get around this fact. And so power supply becomes a critical constraint. In many industrial Internet of Things edge devices, it's not always the case, but in most cases it is so. The other part which sort of again affects the power supply is communication. So when you talk about the IoT, right? I mean, most of the times your communication, you'd be aware of that. It'll be either over Bluetooth or a Wi-Fi, or I mean, even there are instances where you can have a wired communication out. But in the case of IoT, you're always, it's highly likely that you're these devices are installed in a remote location, and the access to communication is, it's very difficult. So you typically rely on some long range communication, right? Maybe cellular, in rare instances, satellites, even if it is some other sub-gigahertz technology, like let's say a Zigbee or a Z-Wave or any of that, you'd still want, I mean, the distance that you can communicate to is very important. I mean, it'll typically be in the range of a few kilometers. I mean, especially if these devices are remote, and it's a very simple math. So if you have to communicate longer distances, you tend to burn more power. So especially if the frequency is higher. So again, it has a bearing on your power supply design, and so the communication technology that you choose and again the constraints that it imposes are many actually. So your data rates, I mean, there are some things that we'll talk about in the subsequent slides, but that's an important element again, the communication part. Then the reliability. So reliability, of course, I mean, any device, be it consumer or non-consumer device, you expect high reliability. Nobody wants a device that crashes every now and then. But again, because these devices are very likely to be in remote places or hard to reach places, in IoT, the edge design, the edge devices have to be very reliable and rugged, because there is very little that you can do if something goes wrong. So your hardware design, the software design, and everything has to be very well thought out to ensure that the reliability that customers desire is delivered. So that's an important piece. And the last one, which is important no matter what the device, or whether you talk about the consumer IoT or the industrial IoT, is security. Because the security vulnerabilities, right? I mean, they've always existed. I mean, ever since we've had software and connectivity, security has been a key factor that people worry about. I mean, everybody knows about the number of vulnerabilities in the earlier operating systems and how companies have progressively corrected them over a period of time. But every now and then, always the security vulnerability pops up, which gathers a lot of media attention. Now, the problem with IIoT is again, it's much more intense, because if some of these devices are installed in some critical infrastructure appliances, and for instance, if you're monitoring, let's say, a oil refinery, or you're controlling, so these are not just sensors, right? I mean, they could be actuators. You can actually use them for your process flow. So if anybody gets into your system, the amount of damage a person could do is enormous, and it could be life-threatening in the case of IIoT. It is obviously a concern even in the consumer space. For instance, if you have a security camera at home and somebody hacks into it and they're able to view the videos, or tap into the link, that's a privacy concern. But very rarely does something become life-threatening. In the case of IIoT, there are many instances where something can cause a lot of financial and maybe damage to life. So that is again an important piece of IoT, which we'll have to consider. All right, so moving on. So this is a industrial IoT stack. I mean, and when I talk about, so except for those differences, when you talk about the stack and when you talk about the stack and the design of, the different layers in an IoT stack, it remains the same whether it is industrial or a regular IoT stack. So I'll talk a little more on the industrial IoT stack here. So there are 6 layers. I mean, if you look at it very broadly, you have the sensors at the bottom, then you have the edge devices, then you have the gateway, the cloud, the insights, and then the consumption layer. So we'll just talk a little about each layer, and then we'll talk a little more on the architectural elements in each layer in the subsequent slide. So at the lowest level is sensors, right? At the end of the day, IoT is what? You're connecting things to the internet. So when you talk about things, I mean, these are like, I mean, you could probably monitor temperature, you could monitor pressure. I mean, you could monitor all kinds of. It could be simple digital on-off. You're probably monitoring the level of your light, and then. So there are a lot of, and when I say sensors, I mean, it can also probably just spill over into actuators, right? You would probably want to turn something on or off remotely. So these are the, I mean, the dumbest things that in your layers of an IoT stack, these are the actual things which do something, which are connected to the physical world. And then on top of it, you have the edge. Now, this is where the computation power comes in, because you can have a very simple sensor which doesn't have any computation power, which just translates a physical element into some voltage or a current or a digital level, which can be interpreted by something on the edge, where you can run algorithms, where you can have intelligence built in and the connectivity built in to allow this data to go out into the wider world or into the cloud. So that is your edge device at the next level. Then you have the gateway. While edge devices themselves in many cases can function as a gateway, I mean, it may not always be the case. Your edge device could be something simple, which is probably has just a Ethernet interface or some other wired interface, or maybe a personal area network kind of a wireless interface, but it may not be enough for it to reach out beyond the confines of your home office or I mean, wherever the installation area is. So that is where a gateway is necessary, which allows you to plug those edge devices and your sensors to the wider cloud and to the wider world. So that is the gateway. And in many cases, I mean, the line between sensors, edge, and gateway can get blurred, especially when the devices are more powerful. If you look at some of the development kits, I mean, I'll come to it too in the later slides. I mean, they have a lot of these features baked in, and they probably still need a sort of a wireless access point or something. But if you have a cellular radio, maybe you don't even need that, and you can just bypass the gateway and directly get onto the cloud. Then you have the cloud piece, right? So the cloud is, I mean, anything that's out there, I mean, installed on the internet, which is remotely accessible via the gateway for your device. So which is where all your logic lies. I mean, when you have like hundreds and thousands of devices connected, this is where your applications run, and so you could have it could be Azure or Amazon. I mean, there are a plethora of cloud operators there now, and so this is the piece that L4 is the cloud piece where you can actually have your operating systems and your applications running. And on top of it, you have the insights, right? Okay, what do? You have all this data. It's come into the cloud. You probably store it somewhere, but then what do you do with it? The idea of IoT, like I said, is ultimately you'll have to derive some benefits out of it because of the connectivity, I mean, and the data that is available with you. Then you analyze it. Maybe you analyze it for patterns, I mean, or for rules or anything that you deem fit. And then you draw insights, which can then either be driven, I mean, alerted to customers or, I mean, whoever is interested in the data, or you could act on it, right? I mean, you can crunch this information and take decisions which are again driven down the stack back into those actuators, right? You could, based on a condition that a sensor has reported, maybe you turn something off. But those are very simple things which an edge device can do. But when you talk about insights, I mean, maybe this is, you know, that there's this pattern. I mean, you've seen this failure before by analyzing previous failures. And so when based on the patterns, you can draw additional actions that you can drive down. And then these can also be presented upwards, right? I mean, somebody can consume that. You can expose APIs where someone can subscribe for these events, or you can write additional rules, or you can plug into, let's say it's an industrial IoT. I mean, you can plug into your ERP systems, and there are a whole lot of things that you can do at a higher layer. So these are I mean, broadly the 6 layers of the IoT stack, and the role that each of them plays in ensuring that actionable insights are delivered and acted upon. So when you talk about the architecture, so it's again, I mean, whatever I've explained in a little more level of detail. So you talk about the devices, right? And then when you talk about edge applications, so you have the devices which are various sensors, actuators, and all that, which actually are connected to the physical world. Then at the edge level, you could have applications, you could have actions, you can have alarms. You can say that the temperature that the thermostat reported is above a certain set point, and so that's probably an alarm condition because it is not expected. Then you have backup and recovery of data. So if something goes wrong, I mean, you would want to probably come back to a safe state. So these are things that you can, you'll have to address in your application. So when you have the devices, then you have these applications, and then you talk about the communication. Now the communication is, like I said, it's at various levels, right? It's between your sensor to your edge device to your gateway to the cloud, and then you can have customers consuming the insights, at a higher layer through an API. So communication broadly, you can consider those APIs that are available. It can be for notifications, for general mobile API, cloud API. So you can wrap your communication across over various APIs. And then you have the cloud infrastructure that you'll again, so when you talk about the cloud infrastructure, you have the compute piece, right? There is a piece that runs all, which is the brains of the like the operating system, and then the middleware and the applications that run on it. And then you have the network piece, because you have a plethora of devices connected. You need load balancing. You need to know how much capacity you have, how much bandwidth you have. All that will have to be planned as the network piece of it. And then you have storage. When you have all this data coming in, how do you store that, right? And in what form do you store the data? Do you have relational databases, non-relational databases, and they have to be easily accessible, and not only for others to consume, but for you to probably build good dashboards, and insights. So the storage is again a very important piece. And how much would you store, and where would you store? How would you store? So that becomes an important architectural element again. So then you have various platforms that you build over top of it, right? You have something to manage your assets, because all these devices are what they control or what they connect to. There are probably assets that you would want to monitor, control, manage. And then you have data. So all the data that flows into your cloud, what would you do with the data, right? You will have to aggregate it. You'll have to store it somewhere. You need adequate mechanisms to query it in a form that is later utilizable in the higher layers. And then you would need some kind of a management, right? When you talk about, for instance, mobile devices, you have something called mobile device management, where you can drive some actions. You can configure the devices remotely and change configuration parameters. So there's a management piece to it. And then you have, on top of it, you have analytics. I won't go into the details of each of that, but I will just broadly cover what the architecture of such a system would imply. So then you have an analytics piece where this data is crunched. Then you have, analytics you can do at a very minimal level using some rule engines or running some very plain vanilla analytics, or you can go much deeper. And for those of you interested, you can go and look at machine learning. And there are a lot of things that one could do once you have the right data with you. And then there are, when you have to derive insights, because that is where this analytics piece, and then the science of either prediction, data science, or decision, they become important, because ultimately the benefit of this is only realizable if you can draw meaningful insights. And what do you, when you draw insights, what do you do, right? Either I can go, for instance, I have let's say remote telemetry units monitoring a large asset base. I can just probably, as an operator or somebody who runs this organization, you can go log into a screen and look at the dashboard and look at the health of each of those devices, look at the data that they're reporting, look for trends that are out of the ordinary. And then maybe you, as a service provider, you can deliver reports to customers. Either they could be real time, or offline reports that are delivered. And then you can explore, you can expose APIs to other developers, right? For either a fee, or depending on your business model, which they can use to integrate with either their applications or build other cool stuff using your APIs. So this is the architecture of IoT, and the stack, and how you would typically go about from considering the various aspects that need to be covered. And obviously, the piece on the right that you see is the security and encryption, which cuts across all your layers, because we'll talk about some of the security practices and what you need to do for data at rest, for data in transit, and how you provide access to data. So this is a so after all this, now we'll get to the edge part of it. And so what is an edge device, right? So this is just a definition that I found from O'Reilly. It's a wide array of sensors, actuators, and devices. These are the system endpoints that interact with and communicate real-time data from smart products and services. So that's a definition. I mean, but anything that interacts, like I said, I'm kind of blurring the line between a sensor and an edge device, because a sensor in itself is just a very simple element that has to interface with something. So we'll talk more on the edge devices here. All right, some of the integration challenges that you run into IoT, let's quickly talk about it. One is, we've spoken about it a little in the previous slide, so I won't dwell on the points that we've already covered. But one is limited connectivity. I mean, many of these devices, the connectivity, even when they are connected, right, it is not that because of battery life constraints, because of the communication costs and all that. It is not that, it's not like a regular consumer devices that is connected always. So the connectivity is extremely limited, and your design has to cater for that limited connectivity that an edge device has. Then you talk about real-time response. So many of these devices in the environment in which they operate, the decisions that have to happen, the applications that run on it, there's a real-time response expected there. You cannot act on it. I mean, even in many cases, right, where there are very hard real-time systems, even delay of a few milliseconds and all that can be catastrophic. So that's the reason why this becomes a challenge. Is when you're talking about connecting this to the cloud, you have limited computing power, and you have to ensure that your real-time characteristics of the device are not compromised in your goal for connectivity. So that is where the real-time response becomes a challenge. And also, if you're offloading decisions from the device and you're taking them elsewhere, then the decision has to be driven back in real time in many cases. So that causes its own set of challenges. Then you have cost of communication. For instance, I could put a cellular radio. Let's say I have something monitoring again in let's say gas pipeline somewhere. So it's very unlikely that sometimes I'd even have cellular radio, right? Maybe a satellite link is the only option. But then satellite communication is extremely expensive. So what is the value that you would derive from a solution like this, and what is the cost that you're willing to shell out for communication? Because at the end of the day, the data that you get out of it should be valuable enough to pay back the cost of the communication. So your designs have to cater to this cost, and bear in mind that while you have limited connectivity, the cost of communication is again another hindrance that before you can really come and launch a IoT solution. Then obviously we have spoken about the power supply constraints a little while back. So that again remains a very important piece. And then you have very limited computing power. In many of these edge devices, the amount of, I mean, they do not run multi-core, multi-gigahertz processors. I mean, in many cases, they'll be very simple processors, right? Where maybe it's a core with a few megahertz or a few hundreds of megahertz worth of computing power. So you have to use it very judiciously, and the designs have to cater for that limited computing power. And then you have limited memory, be it the RAM or the flash. So your binaries, I mean, the size of the application you build, I mean, the size of your firmware has to be extremely tight, and you have to be very judicious in the use of your data structures. Your runtime memory that is available to you is extremely limited. So these present unique architectural and design challenges that you have to be very aware of, because for people who are not really from an embedded kind of a background, I mean, these constraints can be really very novel, right? Because these are not typically things that you run into when you're developing applications on the cloud or even on a PC. So these are some of the integration challenges that one should bear in mind. And one of the last ones that which I referred to in the previous slides, was very limited human interactions. So the reason where this becomes important is when you talk about your design of your edge devices, they have to be like self-sustainable. I mean, if they get into a deadlock, I mean, there should be a way to unlock it, or there should be a way to reset it. Your watchdog timers, I mean, I hope people are familiar with these concepts, but you can look it up if you're not. So you need a very good watchdog timer design that can monitor the state of your applications, realize that there is a deadlock or an out of ordinary condition, and then cause a reset, a reset which allows the applications to come back to again a state where they can continue to execute and perform the tasks that they had to. So put together, these constraints make the edge device part of IoT very interesting and very challenging. But of course, I mean, there are various ways to solve this problem. There are many ways to skin a cat. So And it depends also on the kind of applications that your devices and your solutions cater to. So in some cases, like consumer devices and all that, I mean, some of these constraints still apply, but in a limited level. For some very remote, very low power solutions, I mean, some of this become much more pronounced. All right. So when you talk about, we'll quickly talk about edge device communication. So I've just listed various categories, right? So you have communication from the sensor to your edge device, and then you have communication from your edge device to the cloud or to the gateway. And then you have protocols, actually. I mean, so these are the physical communication mechanisms that you have in place here. And then you have protocols that you would need, that the application would utilize to send messages back and forth. So when you talk about the sensors, I mean, these are, when you talk about sensor communication, you can have either wired or wireless, which is where I've listed a few. I mean, I'll talk about maybe just a few of them in the subsequent slide, but we cannot touch upon all the communication techniques that are listed here. But one very important thing to bear in mind is some of these, for instance, like a ZigBee protocol that I talk about for connectivity could equally apply for, I mean, when I talk about connectivity in the middle, the section there, it is more for from the edge device out to the cloud or to a gateway, but it could equally apply for a sensor. I mean, you have ZigBee-based sensors or lights, I mean, all kinds of things, right? Same thing with Z-Wave. WLAN probably is not so popular for sensor communication, but nevertheless. So it's a thin line sometimes, but when you talk about something like a Modbus or a wireless HART or a BLE, it's very unlikely that you would use those communication techniques for anything other than a sensor to a edge device communication, because I mean, they're typically low throughput, I mean, low data rate and low range, actually. I mean, the very short range communication techniques, which you can use for sending some data from sensor, but nothing beyond it. And some of them are not even two-way, right? I mean, so they have their own constraints. And then you have the protocols that run over on top of this, I mean, on your stack. So the protocols, so we'll talk about a couple of the protocols also. So BLE, I mean, which is Bluetooth Low Energy. That's a very popular standard that's emerged because Bluetooth, I mean, used to be, Bluetooth had this advantage that they already were quite ubiquitous, and they had installations on a variety of devices like mobile phones and all that. They came up with a low energy variant because Bluetooth was quite energy. It was a power hog, and so BLE solved that problem, but it obviously at an expense of data rate, and it operates in the 2.4 gigahertz ISM band. ISM is industrial, scientific, and medical band, which is a free band, right? You don't need a license to operate in the spectrum, which is where the Wi-Fi also operates. Then you have ZigBee. ZigBee is again a very popular standard for personal area networks. It again supports data rates of theoretically around 250 kbps, and it is based on an IEEE standard called 802.15.4, which is the PHY and the MAC. And ZigBee has the network and the other layers on top of the 802.15.4 PHY and MAC. So this is a very popular standard. And so the reason some of these standards also don't, I mean, they didn't take off in the way they were expected to is you need they're not directly compatible with TCP/IP, which is a ubiquitous networking standard out there, right? So there's a variant of, so there's a 802.15.4 standard called 6LoWPAN, which has the IP stack over 15.4, which is probably more usable, but you would still, the physical radio is not compatible with Wi-Fi or anything. So you'd still need a gateway to finally get onto the actual network. So in many cases, some of these factors limit their adoption. And then you have, in the industrial space, you have something called wireless HART. So as you can again see, it's again based on 15.4, 802.15.4, and it's a wireless sensor network used in the industrial space. Sorry, that repeated twice, but, and then you have, so WLAN or Wi-Fi is one of the most ubiquitous communication technologies out there, but it is never taken off in this edge device or the sensor communication part of it because of its energy requirements. I mean, it is quite power hungry, and the protocol is designed in a way where it's very hard to make it less power consuming or more power efficient. And so there's a new 802.11 standard called HALO. It's called 802.11 HALO. It's a sub-gigahertz WLAN. Otherwise, Wi-Fi operates in the 2.4 gigahertz band, but this particular standard operates in the sub-gigahertz 900 megahertz band. And I mean, for those of you who have studied communication, right? I mean, the lower the frequency, I mean, the greater the range for the same amount of power that you use. So it obviously has extended range, and also it consumes lower power. So the standard caters to it, and people expect that 802.11 AH to really take off in the near future. Then you have the then you have a set of standards, I mean, including 802.11 AH and narrowband IoT and LoRaWAN. So these are called low power WAN technologies, right? WAN is a wide area network. So as opposed to WLAN, which is a wireless local area network, there's WAN as a wide area network, and LoRaWAN, narrowband IT, and even to an extent 802.11 AH are actually low power wide area network standards, which allow you to communicate over large distances. So even for instance, if you have Zigbee or 802.11 or any of them, I mean, you still have this problem that you need a gateway or something to finally get you onto the cloud. But in the case of LoRaWAN or narrowband IoT, which is a cellular standard for low-rate devices now, so you can directly actually reach out to the cloud, because I mean, these are standards let you communicate over a very wide distance. I mean, maybe in terms of kilometers, right? So this is an area, very interesting area, which will have an impact on I mean, on how these devices will be designed going forward. So, and a couple of, I just wanted to talk about a couple of application protocols, because we cannot cover everything here, but one is MQTT. I mean, this will be the probably the most ubiquitous standard that is being used for messaging or for communication in IoT, and that's MQTT. And it's actually a very lightweight publish subscribe messaging. Actually, I mean, you have a broker and then you have a MQTT client, so you can publish your data to the broker, and then you can have the broker can have subscribers who then get those get the data that has been published. So that is the MQTT. And then you have another standard. So while MQTT is a messaging broker-based standard, there's another standard called COAP, which is Constrained Application Protocol, which is it's similar to HTTP, but while HTTP is based on TCP, where you need to open a session and keep it active, COAP is based on UDP. So it's sessionless in that sense, and it's a document transfer protocol. But the difference, obviously, between MQTT and COAP as well, COAP is a request response standard, right? Like HTTP. I mean, you do a get, and then you get a file back. You can do a put, post, delete. So these are all the standard REST operations that you could do with HTTP. So COAP is something similar, but MQTT is more of a messaging standard. But I mean, and most of the cloud operators out there and or devices, a lot of them, there are many MQTT clients and brokers available. Then we'll very quickly talk about security, edge device security, right? I mean, there are security principles that you would have to adhere to. I mean, in terms of you need ways to authenticate the device, you need a way to authorize the device, and there have been there's been a lot of attention around security, primarily because of the number of attacks that have happened, and a couple of them are mentioned there. Stuxnet was a very famous attack, which was actually it was not an IoT space. I mean, this is more of an offline attack, but there was a worm that infected the control systems. It was actually a Siemens PLC, I think, which was used in centrifuges and for uranium enrichment, actually. And so the worm very quietly, I mean, it went and damaged the centrifuges, which set back the uranium enrichment process of our country by many years, right? So Stuxnet, I mean, for those of you interested, you can go there. I think there's a movie on it now, and it was a very famous attack. Then there was Mirai, which was again a distributed denial of service attack. So a lot of the industrial devices, they always had default username and passwords, right? And so this used to infect PCs, the Mirai worm, and then it'll go and just try this default username and passwords on all these connected devices. And once it finds that, it'll go and infect and start a denial of service attacks on whatever servers they were connected to. So that was a very famous attack. So some of the things that we have to address, right? I mean, one is you'll have to make sure that you have your device, embedded device, has secure storage. For instance, if you're using any keys or anything to encrypt your data, and that key is leaked out or somebody can read it, then you're in effect compromised, right? So you need a secure storage where the key cannot be read out by anybody. Then you need to make sure that there are no interfaces into the device where somebody can just plug in a wire. I mean, like you see in Hollywood movies, right? They just plug something into some reader and suddenly, voila, they have all the data that they need. So that is again another design consideration that you have to take, where you don't let anyone access your device. So your JTAG ports, I mean, all that have to be fused so that nobody can access. Then you have connection security. So when data is being transferred, you have to make sure that it is protected with SSL, and so you can have client certificate to authenticate the device to the server. So some of these mechanisms can really help you protect your data while it's in transit, and also to authenticate your device to the server so that the server doesn't allow unauthenticated devices or unauthorized devices to connect. Then you have secure boot, which is again, when you're booting your firmware, I mean, there has to be, otherwise somebody can put some malicious firmware and make your device boot. So secure boot ensures that only signed firmware is booted. So there is a way to sign the firmware, and the bootloader recognizes the signed firmware and then allows that to boot. So these are some security aspects to consider. I'm sorry, once in a while some window keeps popping up. So if somebody is getting started out there on IoT, right? So there are some, I can talk about a few things here on how you would want to get started. So the first thing you can do is get a development board. So there are a plethora of development boards out there. I mean, especially the most popular ones right now are a Raspberry Pi or an Arduino. So a Raspberry Pi is actually a very powerful computer. I mean, it has a 1.2 gigahertz ARM-based core, and it has all kinds of USB ports, and it has GPIO connectors, which is general purpose IO. So you can connect a variety of digital inputs. Arduino is actually a much more lower end. I mean, the actual board is much more lower end, where it supports many digital inputs, digital outputs, and also analog inputs. So it's for IoT kind of applications, or for actually connecting sensors or different kinds of sensors, Arduino is very well suited. And Arduino now, the Arduino Yun, I mean, there's another board which actually has a Atheros 400 megahertz processor, which also has a Ethernet connectivity out. And in fact, if you go to the Arduino site, you will find a lot of them with even Wi-Fi connectivity and other options. So you can use the power of the Arduino, where you can connect with a variety of sensors, I mean, be it digital or analog. And then you can also drive outputs using PWM, which is pulse width modulation. So where you can probably drive things like, you can change the brightness of LEDs that are connected, or you can connect a stepper motor out to it. And so that it allows you to do a lot of things. And so these are two popular choices that I would recommend. And then obviously on the cloud side, you can look at AWS and even Azure. They have this IoT. AWS IoT is this is from Amazon, and then you have the Azure IoT Edge, which allows you to connect edge devices. And in fact, if you go to their sites, I mean, they also have tutorials on how you can connect a Raspberry Pi to the board and what you can do with it, right? You can write a very simple script, I mean, and probably just do a hello world, or you can, and they also, there are pinout diagrams. Even Google has some of these on their site, actually, where you can say what you can do with a Raspberry Pi when you connect it to an IoT. I would recommend you just connect a very simple digital input, I mean, do an on-off kind of thing, connect it to the cloud, and there you can run a small logic that based on certain on-offs or something, you can drive an action back, where you can probably do something as simple as glow an LED on the board. So that would be a very nice way to get started with IoT, because it's a beginning of a very long journey, right? There's a plethora of things you can do out there, but I just wanted to touch upon a couple of things that you can do to get started. And then there are a couple of things that are quite interesting. There's a company called Electric Imp, which gives you Wi-Fi modules that you can connect it to a dumb device and it becomes a IoT-enabled device. And there's a company called Tembu. I mean, if you go to their site, you'll find a lot of interesting IoT projects, right? They'll talk about water level monitors. I mean, various IoT ideas that they have put out there. And they also talk about, and they have this, they actually have a complete stack, right, on how you can connect and do things. And they tell you how you can do something with an Arduino Yun board, actually. So that'll give you a lot of ideas. And the SDKs, I mean, they have stuff available. They have free trial, limited period trial also available. So that's, again, I found it quite interesting. Even Electric Imp does, but I think they target more manufacturers and small vendors who otherwise do not have the wherewithal to develop IoT applications. So a few functions, I mean, or APIs that one could develop are, I mean, so what would you do with on an edge device, right? You probably have to register the device at a bare minimum. And when you're talking about developing IoT applications and running something on an edge device, I mean, you would want to do registration, you would want to do remote firmware upgrade, because one of the most critical things about when it comes to security that we spoke about is the ability to upgrade firmware. That's the only way for you to patch any holes that are discovered on your device. So firmware upgrade is a key feature. I mean, which many always tend to underestimate, right? I mean, how important a firmware upgrade is. Then you have events and alarms. So when something happens on the device, someone should get to know, right? So there are APIs that need to be developed for event streams and alarms. And so it could be based on a publish subscribe mechanism, or you can keep a stream open and there could be a listener that's continuously listening to those streams. And then obviously remote command and control. You would want to control, maybe turn something on, turn something off, move something. I mean, maybe an actuator, right? I mean, which is in an HVAC system, you would want to turn on the damper. So there are a lot of things that you would want to do remotely. So there are APIs around it. I'd love to list some APIs, but if you look at some of these categories, you'll find a lot of sample APIs out there. So please go ahead and look it up. So I'm coming towards the end of the presentation. So one of the things that I wanted to touch upon was analytics, right? So you have these edge devices, you have all this data going into the cloud. So one of the things that you could do is really look at analytics. I mean, so what do you do? One is based on the data that these devices supply. And the other analytics that you could do is, I mean, based on the data that the device themselves have, right? How many times does the device restart? I mean, what kind of logs does it have? So if you look at some of these conditions, right? I mean, these are very good data points to analyze and draw actionable insights. I mean, this has nothing to do with probably your business logic, right? This is just data that you're mining from the device. So you can look at memory diagnostics. I mean, did it crash? Did the memory overflow? I mean, what are the device log? I mean, what is the battery health? I mean, does the device battery need to get replaced? How was the device used by customers? Or what are the environmental conditions that it has been subjected to? There's a lot of data that one could mine from the device. And you could use that to again draw insights, right? You can talk about diagnostics. I mean, you can talk about device maintenance. Based on your connectivity issues and mining that data, you could look at how would you optimize your network infrastructure. So there are a lot of things that one could do based on this analytics. So in fact, there's a stream of, I mean, while this is talking about just the data that a device would supply based on its conditions, there's an area of computing called edge computing or fog computing, as Cisco calls it. So this is so because it's so expensive and the volume of data from like these billions of devices could be just unmanageable. So you can move the analytics closer to the edge actually. Instead of doing everything in the cloud, I mean, you can move it closer to the edge. It's called edge computing. And Amazon IoT, for instance, has something called AWS Greengrass, which does that actually, which lets you, they have a set of functions called, I mean, they have, if for those of you who can go into AWS and read it, I mean, there's Lambda functions. So they talk about Lambda that can be done closer to the edge, and you can take real-time decisions. Even when there's no connectivity to the cloud, I mean, you can have some local communication enabled. So some of those things, so there's and other cloud providers do have that, but because Amazon, I mean, I was able to recall that I just mentioned it. So you can go and look it up, Amazon AWS Greengrass. And so this is edge devices and the analytics, whether you do it on the cloud or closer to the edge. I mean, that's again an architectural choice, but there are a lot of things one could do. So towards the end, I'd just like to talk about one example, right? Which in the previous slide, when I talked about this insights that one could draw just from the data on the device, there is this, Honeywell has a workflow performance solution where you have this voice headsets, which if you see these workers in warehouses, some of them, I mean, their workflow is decided, right? And then they're told to do certain things and it's laid out in front of them. And then they have these headsets where voice instructions are given so that they know what to do next in the workflow. And the worker can respond back by talking into it. There's a microphone there which understands what the worker says. So the system is trained for each worker. So for language, I mean, for the accent or the way the worker pronounces certain things, there's a vocabulary. So the good thing is, I mean, now the workers' hands are free, right? They don't have to look at any device or any chart or anything, and they can just utilize that to go about their workflow, picking, sorting. I mean, whatever they need to do in the distribution center or any place they could use for maintenance and inspection. So there's a product which which mines the data that these devices have, right? And then they draw some very interesting insights. So they can tell you, based on the data, how many workers are going into incorrect locations. Where you go and you try to pick or put something, but you're at an incorrect location because you didn't follow the instructions correctly, or probably the instructions were wrong. This is a very expensive thing, because in a distribution center or a warehouse, any time wasted, is very expensive. So they can look at when they went to incorrect locations. And if there's something called check digit. Actually, check digit is, it is a locationing thing in a warehouse, right? It'll be a digit where it'll tell you what the location is. So if there's any how can you enhance the performance of that, right? How can you do the locationing better in a warehouse for enhanced productivity? Or if speech recognition performance can be optimized. So they'll look at how many times there was a problem recognizing a pronunciation, or should the vocabulary be richer. So there are some of those things that can be again mined. Now all this, see, the device is meant to do some workflow operations and ease workflow operations, but just by mining some good data from the device, you're able to draw a lot of insights. So analytics, while they can help solve a business case, they can also solve many other, help optimize a lot of maintenance and operational things, which again is a beauty of how this entire system operates, right, in the IoT space. And again, these are design decisions that one must take when one is designing such systems. So I just want to touch upon this analytics piece towards the end, so that you understand, right? While it is all very well, we looked at ways to connect, the benefits of connectivity, various technologies that one could use, how to get started and all that. At the end of the day, the power of it is the insights that you would draw from all this data and how you act on it. So I think that concludes my presentation, and now I'm open for questions. So let me just expand this. Sorry. Oh, there are a lot of questions here, so I'll have to very quickly. So somebody has asked, architecture-wise, is there any difference between IoT and IIoT? And I spoke about it, right? There's not a big architectural difference between IoT and IoT, but it's just the things that you need to take care of. While you're designing an industrial IoT system, there are many more constraints that are imposed on it, and we've touched upon it. I hope that answers the question. And if somebody needs additional details, please drop me an email. I'll just note down my email address here and in the end. Does the data management comes under data analytics? Yes. I'm beginner to IoT. How can IoT be combined with machine learning? See, machine learning is, again, like I said, it's an interesting space, right? Where you when you have all this data that is put into the cloud, you can write algorithms that analyze the data. But when you talk about machine learning techniques, this is where the machines themselves, they mine the data, right? Then you look for patterns, you look for actionable insights. But for that, the volume of data that you need would be really large, actually. So when you talk about consumer devices and all that, when you have that kind of volume, right? When you have like terabytes and petabytes of data, that's when you can start inferring and drawing much better insights. Because if you have a very low volume of data, I think a machine learning algorithm will find it very it's very difficult to analyze that and come to any useful conclusions. And how Honeywell cybersecurity plays a role in IIoT. I've touched upon the cybersecurity part of it. It is a very important piece of IIoT. And when you talk about what role cybersecurity plays, it is to ensure that a system is designed which is not easily penetratable. And sorry, again, which is where the data at rest and the data in motion are all taken care of, right? I mean, you should not have any vulnerabilities in the system. There should be nobody who should be able to get into the system, and nobody who can mine the data and get, extract data out and leak anything to and cause any vulnerabilities within your network or your device and cause any damage to the assets that they are monitoring. How much of the discussed technology is open source and paid? A lot of the technology that has been discussed, I mean, a lot of it is open source, right? I mean, if you see, when Microsoft is, if you go to the Git, I mean, they have, if you look at Azure IoT Edge and all that, there's a lot of artifacts that they've put in. In fact, if you look at a lot of these companies like Node-RED, I mean, there's again a standard there, I mean, where you can connect these devices and you can create some flow diagrams and all that, and run logic on the devices based on that. It's a visual tool node, right? So and a lot of the technologies are based on, I mean, the operating system is Linux. I mean, you have these message brokers like MQTT message brokers, and clients are open source. I mean, the stacks are open source. Even when you have to connect into the cloud, I mean, there are a lot of providers out there, I mean, who let you I mean, free trials, I mean, to try something off even in the commercial offerings. So I would say predominantly a lot of it is open source. Obviously, I mean, it depends on but for you to get started, I don't think there's anything that holds you back. I mean, it doesn't have to be commercial for someone to get started with. And I think I'll take just a couple of questions more, and then I'll probably respond over email if I can. How to optimize the amount of data transfer to the cloud, and so okay, there's a question on how to develop interesting new projects in IoT. Like I was talking about this company which is Tembu. I mean, that's why I mentioned it. I mean, if you go to their site, you will find some very interesting IoT use cases which you can try, right? And some of them are very simple, actually. I mean, it's monitoring moisture level in soil, monitoring level of water in a tank. And so there are, I mean, many of them. I mean, if you just search for IoT use cases and all that, you'll find a plethora of devices. And how do you so, okay, there are many other questions, but I'll quickly take a couple more. So how do you reduce the cost of communications and data storage? So like I said, I mean, the communication cost, I mean, when you talk about, you cannot offload all the computing from your edge device out to the cloud. I mean, that is the fundamental rule in minimizing your communication cost. I mean, if you start sending all the data that you have and expect all the minor decisions to happen in the cloud and then have the actions driven back, I mean, your communication costs are going to balloon, actually. So that's where this edge computing piece of it, even if you don't have a fancy edge computing algorithm out there, most of the what you should aim to do is try and act on as many things as you can locally, and have, for instance, if you start reporting, let's say, your network strength, right? I mean, your Wi-Fi signal strength every few seconds to the cloud, hoping to draw some insights from it, it is just a waste. I mean, you should decide on the periodicity and say, okay, it's very unlikely that my Wi-Fi signal strength would vary every 10 seconds. So maybe I can do it, I mean, every 10 minutes or maybe every hour or something, just so that I know that if there's an out of ordinary event, I mean, I get to know. Or if the signal strength drops below a certain level, only then will I send something out. So there are certain decisions that you need to take in terms of minimizing communication cost. All right, and what is the difference between IoT cloud and M2M? M2M is, so IoT, we just spoke about it. Cloud is the piece, I mean, your computing infrastructure that is on the internet, to which all these devices are connected to, and where you can run applications and algorithms that can help you, and where you can host solutions, and where you can expose APIs that customers or any developers can connect and draw some inferences from. But M2M is machine-to-machine communication, right? So I mean, this is where two machines can interact. I mean, for instance, if you have a system which, let's say, I mean, something that's connected to a sensor, and there is some actuator or something, and there is a local connectivity available between those without necessarily going to the cloud, you would know that if the sensor, let's say the temperature goes above a certain level, maybe I'll have to turn on some damper to allow cool air to come in. I mean, if that's a kind of decision, I mean, that's a very simple machine to machine kind of a communication where there's no there's no other broker or nothing in between, right? I mean, at a very simple level, that is what it is. So even here, I mean, when you talk about all the sensors and all that, I mean, machine to machine can be anywhere where there's no human interaction, right? I mean, anything that where a device communicates with another device can be classified as machine communication. So a lot of these are, I mean, it depends on how you define it, but that is what M2M is, and it's a very broad umbrella term. Okay, I think I'll take one last question. Is FTP also used as a popular protocol? FTP is a popular protocol, but not for see, the problem with FTP is it's just a file transfer protocol, right? I mean, and then there's something called even TFTP, which is trivial FTP, which is probably a little more lightweight. But then you can only get a file. The problem with many of these things is unless there's a two-way communication, there will not be data exchange that happens. So when you talk about FTP, all you can do probably using an FTP is maybe if I have to get a log file out of a device, I mean, maybe I can do an FTP, but then that's not an ideal way to do it. I mean, there are many other ways to send log files out. I mean, if you have any messaging system or any of these protocols implemented, you can still do that. But yeah, FTP is not necessarily the best way to do is not the best protocol to use for our IoT systems. Okay, so I think there are too many questions to still listed here. I don't know, maybe I'll have to ask somebody at HackerEarth what is the ideal way for to answer this. I'll try to list them down and probably post them somewhere where you can look at the answers. But yeah, so because we have run already 10 minutes over time. Thank you all for joining, and I'll get back on because I have the list of questions here. It's just that I'll find a way to answer and get back to you on those. So thank you for joining. You all have a good day.